All right, if I could have your attention. This is, this relationship involves a quantity that we have done really nothing with to try to define. And this is where I'm talking to my advanced physics students. This charge, measured in coulombs, charge is one of those quantities that I find it very hard to define, if not impossible. How do you define charge? And that's where I'm going to look to my physics students. What is charge? Like in AP Physics C, you spend an entire semester talking about charge because you're doing electricity and magnetism, right? So it's all saturated with charge. Okay, I'm seeing the smile, Joseph, and you're looking back at Maddie, hoping, okay. Can you define charge?
Maddie, help me out.
Maddie, charge. So we know electrons are charged, neutrons are not. Some quarks are charged, protons are charged, but, so okay, some things are charged, some things are neutral. What does charge mean? It's a property what? This property that something has. You guys, I don't mean to make you feel embarrassed. I don't want you to feel embarrassed at all. Because I am stuck trying to give you a definition of something I can't really define. And so here's my very lame definition of charge, because that's what it is. This is terrible. I'm going to tell you that charge is measured in coulombs, so that's the unit for it, but that doesn't really tell you what it is. And we know that electrons are charged, and it turns out this is measured. 1 mole of electrons has a charge of 96,485 coulombs. But does that define what charge is? No, you don't know any better now than you did before I uncovered that, what charge is. But that's the funny thing about charge. And I don't think of any physical property or any physical quantity that's harder to define than charge. The only thing that I think rivals charge in terms of its difficulty in defining, and this is going to surprise you, time. Can you define time? You know what I mean? Like, how would you define, if you had somebody from another planet or whatever come and you were trying to define what, or describe what time was. I don't know, look at the clock, right? Well, that doesn't really define what it is. So anyway, charge is kind of the same way. You know it's there. Time exists, I guess. What's that? Yeah, right. So yeah, I guess you could define time like that. But then we're left with charge. So charged things are, they will respond to an electric field. They'll respond to a magnetic field. Charged things will. I do need you to know this number, 96,485. You can round it off to 96,500 if you want to. In fact, this number is given to you in the AP equation sheet. When you do the AP exam, they're going to have an equation sheet there. And that number will be on it. It's going to be 96,500. I do still want you to memorize it, though, because I don't want you flipping for every problem back to that equation sheet. That's why I've had you memorize all of the equations. So whenever in electrochem you see a capital F, that symbolizes Faraday's constant. That's this number, and the unit is not just coulombs. The unit is coulombs per mole of electrons. 96,500 coulombs per mole of electrons. All right. So this Q term right here, the quantity of charge. The quantity of charge is equal to the Faraday constant times how many moles of electrons you have. Like if you don't have 1 mole, what if you only have a half a mole? Well, you'd multiply F times 0.5 to get your total quantity of charge. And that makes the cell potential equal to the work, which is up here, it's measured in joules, divided by the quantity of charge changed into what is equal to NF. So already we're getting someplace in this little baby derivation. What we're looking for is a relationship between cell potential and free energy. Free energy, remember, is delta G. Are any of these quantities equivalent to delta G? One of them is. Which one is closest to delta G? What is delta G, you remember? It's been a while. It's negative RT ln of K. But what does delta G tell us? It tells us delta G is considered free energy. And free energy really is the energy that the reaction will make available to do work. So if delta G is negative, that's how much work can be done by the system on the surroundings. So that term right there, the numerator, that's what we're going to replace with delta G. Now, just something about the sign convention. Remember that useful work is, I should say useful energy, is the energy that the system can do on the surroundings. A system, if it's having work done on it, is not much good to us. But a system that can do work on the surroundings is good. So that means that when work is done on the surroundings, it's identified as negative W. I'm just telling you all this to show you how we get that equation that we're going to end up with. So the amount of work that the system can do is really equal to the delta G term. So when I unveil that bottom line, I'm replacing work with delta G, but it's going to be a negative delta G because it's how much work can be done on the surrounding. And we end up with this. Don't forget the negative side. So we've had a number of relationships that involve delta G, and here's just yet another one in another field of chemistry, electrochem. This is our delta G, an anchor equation. The N, remember, is the unit is moles of electrons. The F is measured, it was defined up here, coulombs per mole of electrons, which is going to cause the mole of electrons to cancel out. And then the epsilon there is the cell potential, which is measured in volts, also known as joules per coulomb. So what happens here is the moles of electrons cancel, the coulombs cancel, and this equation is going to give us a quantity in joules, which is what the unit of delta G should be. Okay, now with this, would you try this? What is the maximum amount of work that can be obtained from the galvanic cell described by that equation? Now, just a comment about the question, lest you be intimidated by all the words. I just want to use the word lest. This, all this, means what? The max amount of work that can be obtained. What are we calculating if we want to try to find the maximum amount of work that can be obtained? That's delta G. Right. So all it's asking us to do is find delta G. Oh, okay. Well, we just learned an equation that involves delta G. Delta G equals negative NF epsilon. Do you know any of the terms in this expression? Well, you know one of them, F. F is a constant. Okay, so we can plug F in, 96,500. N and epsilon, though, we're going to have to work for those. The cell potential, what you're going to have to do is take that table that you have and determine what's oxidized and what's reduced, figure out the cell potential, and then the N is how many electrons are transferred from the oxidation to the reduction. How many electrons were transferred? That's what the N tells you, the number of electrons that were transferred. So I would suggest that you find the cell potential first, given this equation. So you have to figure out what got oxidized and what got reduced. The problem with this one is that there's 4 terms here, 2 reactants, 2 products. All of them have Cl. Okay, give it a shot. Use that reduction potential table. Yes. Yeah, of course. Is the number that are transferred. So you have to find the 2 half reactions and see how many electrons are given off or taken in and set them equal to each other. You know how when we balance redox, you have to set the number of electrons equal, so if you give off 3 and you take in 2, you got to get 6 on both sides. The 6 would be the end.